So today we're going to talk about something called a rational exponent. We've learned how to simplify radicals, but what we'll see is that a power that has a rational exponent is really another way of writing a radical expression. So let's look at our two objectives. The first is, how do we write radicals using rational exponents? And then second, how can we simplify expressions with rational exponents? So again, what is a rational exponent? Well, think about the word rational, right? The first five letters are ratio. So a rational exponent is simply an exponent that is written as a ratio. So x to the 2/3 power, right? 2/3 is a ratio, or you might prefer to call it a fraction, okay? So rational expression is just a mathematical word for something written as a fraction. So x to the 2/3, that's a rational exponent. 16 to the 1/2, that would be a rational exponent. So what is the relationship between the rational exponent and the radical expression? So square root of 25 can be rewritten as 25 to the 1/2 power. Now, square root of 25, even though we don't write it, the index is 2. And so that 2 becomes our denominator in the rational exponent. Let's look at other examples. Cube root of 27. So we could rewrite that as 27 to the 1/3 power. Right? The index 3 becomes the denominator. And one more example. Fourth root of 16, we can rewrite as 16 to the 1/4 power. So the key idea here is that the index becomes the denominator in the rational exponent. Okay, all right. Now, what happens if we have a number in the numerator besides 1? So here's an example, right? Square root of 4 raised to the 3rd power equals 4 to the 3/2. So notice we still have a 2 in the denominator since our index is 2, but the exponent that's in the radicand becomes the numerator in our rational exponent. Here's another one, right? Cube root of x to the 4th. Our index is 3, so we still have a 3 in the denominator, but the exponent in the radicand, 4, becomes our numerator in the rational exponent. One more example, 5th root of z squared. So 5 is our index, that becomes the denominator, but 2 is the exponent in the radicand, that becomes our numerator. So let's state that rule. The exponent becomes the numerator in the rational exponent. Okay, so we can have both cases as these examples show, right? A number in both the numerator and the denominator that's something other than 1. Right, so let's define a rational exponent. And there's kind of two versions of it. One, right, where we are just simply taking the nth root of a radical expression. Our index is n. That n becomes the denominator, 1 over n. Or if we have a exponent that's either part of the radicand inside, or you were raising the entire radical expression by exponent, that winds up in the numerator. That's represented by the variable m here in this example. So let's look at some examples of how we could rewrite this. I'm going to give you the expression that has a rational exponent, and we want to rewrite this as a radical. Notice we have two ways of writing it from the definition up above. So x to the 2/3. Right? Well, we can start by just making the radical symbol with the x inside, but then we can take the 3, right, since it's in the denominator, that becomes our index, and the 2, right, becomes our exponent. So I've written it the first way here according to our definition, where we take the entire radical expression and raise it to the 2nd power. So if I gave you this, how would we say this in words in terms of order of operations? It says, first, take the cube root then square your result. Okay, so we do what's inside parentheses first, and then raise it to the second power or square it. Now, we could also write it this way, right? We still have our 3 as the index, but the 2, the numerator, becomes the exponent inside the radical. And now in this case, we're going to do order of operations in the opposite order, right? We would square x first, do what's inside the radical, and then take the cube root. Now, are those 2 orders of operations equivalent? The answer is yes. It doesn't matter which way we do it, whether we square it first and then take the cube root, or whether we take the cube root and then square it. Okay, it's just like, does it matter first whether we multiply or divide? It doesn't from an order of operations standpoint. So 2 different ways to write it in radical form. Now, as we get further into the unit and we start to work on simplifying or solving equations that have these types of expressions, sometimes it is easier to proceed by using one of these forms versus the other. Sometimes it's easier to take the cube root first and then square it. Sometimes it's easier to square it and then take the cube root. All right, let's get some practice writing this. So I'm going to just pause for a second, let you pause it and see if you can rewrite this as examples in your notes. So x to the 3/5. And for these examples, I want you to write it in both forms, right? With the 2 different ways in which we can show the operation order. So the first form would be 5th root of x cubed, right? So we would cube it first and take the 5th root, or we could write it this way, right? Take the 5th root of x first and then raise it to the 3rd power. Y to the 5/2. So square root of y to the 5th. So we would raise y to the 5th first and then take the square root, or we can take the square root of y first, then raise it to the 5th power. And the last one, 9 to the 3/2. So we can take 9 and raise it to the 3rd power, then take the square root, or we can take the square root of 9 and then raise it to the 3rd power. And this last one is a good example of the order that we do it in makes a difference in terms of how easy it would be to simplify this, right? The first one says take 9 and raise it to the 3rd power. Well, that's 9 times 9 times 9. That's a large number. And then we have to figure out what the square root of that is. Or we can take the square root of 9 first, which we know is 3, and then simply cube it, and we get 27, right? So again, it depends what the numbers are, but sometimes one form is easier than the other to simplify. All right, now we're going to go the other direction. I'm going to give you the radical expression. Can you write it as a rational exponent? So let's do the first one together. So we start by writing a, and then we have a 3 as the exponent. So that's going to become the numerator, and our index is 2. That will become the denominator. Okay, and when we're writing it in this direction, there's only one form that we can write it in, a to the 3/2 power. Let's try this one. So we're going to have b to the 2/5. We're taking the 5th root. Our index is 5. That goes in the denominator. And the last one, cube root of x squared. So we're going to have x raised to the 2/3 power. Now, the easiest mistake to make is to get the index in the wrong place, right? To get the numerator and denominator backwards. So you just have to do enough of these to get your process down. But the key is to always put the index in the denominator first, and that only leaves you with the numerator to put the exponent. All right, now that we know how to write a radical expression as a rational exponent, let's do some work to simplify, okay? And the strategy we're going to use to simplify is to first write it as a radical expression and then simplify, right? We've done lots of practice so far simplifying radical expressions. So 125 to the 1/3 power, that is equivalent to the cube root of 125. And we know that 125 is a perfect cube, right? So our answer there is 5. Let's try another one, a little bit different here, right? 5 to the 1/2 times 5 to the 1/2. Well, we can write this as square root of 5, right? Our index is 2. So square root of 5 times square root of 5 is 25, which is simply 5. And let's look at this last one. 10 to the 1/3 times 100 to the 1/3. So we can multiply this as cube root of 10 times cube root of 1,000. I'm sorry, of 100, which gives us cube root of 1,000. And what is the cube root of 1,000? Well, 10 times 10 times 10, right, gives us 1,000. So we can rewrite that as a perfect cube of 10 to the 3rd, and we get our answer of 10. So rewrite it in radical form, and then apply what we already know about how do we simplify a radical expression. All right, let's have you try a few more here. Here's the next one. And one more. So remember, just pause the lesson while you work these out on your own notes. All right, let's try a couple more here. A little more complex, 64 to the 2/3 power. So we're going to rewrite this. And here we're going to rewrite it in both forms and then ask ourselves, which form do you think would be easier to simplify? Do we want to take 64 and square it, then find the cube root? Now, 64 to the 2nd power is going to be a very large number. I like to stay with small numbers. So let's do the 2nd form where we find the cube root of 64 first and then square it. Well, it turns out 64 is a perfect cube, right? If we look at our sheet of perfect squares and cubes and fourths, the cube root of 64 is 4. Now we square that and we get 16. Negative 32 to the 6th over 5 power. So we can write it as the 5th root of negative 32 to the 6th, or we can write it as the 5th root of negative 32, simplify that, and then raise the whole thing by the 6th power. So 32 is a perfect 5th, right? 2 times 2 times 2 times 2 times 2 gives us 32, except in this case, we're going to get a negative 2. And negative 2 to the 6th power gives us 64. One more here, or at least one more page. 25 to the 3/2. See if you can do this. So square root of 25 to the 3rd, right? Or square root of 25 first, then raise everything to the 3rd power. Well, I know what the square root of 25 is. Let's do the 2nd case. So we get 5 to the 3rd power, or 125. All right, so that's it for rational exponents. Probably the first time you've seen these, but they're not complex, right? We just have to remember that the index becomes the denominator, and the exponent, whether it's inside as part of the radicand, or we're raising the whole radical expression by that power, that becomes the numerator. And to simplify, we just write them as a radical expression first, and then apply what we already know about simplifying. All right, that's it.